Swayam Prabha. Digital India. Educated India.
Let us start with the operators, okay, and continue with that. All right. How many of you worked out the angular momentum? All right. So today we are going to discuss about angular momentum operators. Right. So we wrote the classical expression that L vector equal to R vector into R cross B. It's a vector product, right? I think we derived this on that day. This is equal to I, J, K, X, Y, Z, Px, Py, Pz, right? So I wrote what is Lx. So what is Lx? Lx is Y, Pz, Z, Py, Ly. What is Ly? Yeah, cyclically permute. Y by Z, this by Pz, therefore it is X, Y by, because you have Y, right? Z, Px, Xp. Next, cyclically permute, alright. So you will get X, Py, Y, Px, right. So this is the angular momentum, right. These are corresponding components of the angular momentum in X direction, Y direction and Z direction. These are the components, correct? Alright. So how do you get the corresponding operators? So we said that in the previous lecture, replace with the corresponding differential operators, alright. So you can convert this into operator. Y, it is a scalar, alright, therefore it is scalar multiplication, but Pz is a differential operator. What is the general rule? P operator equal to minus IH cross del, alright. What is del operator? Del operator is I dou by dou x plus j dou by dou y plus k dou by dou z. Therefore, what is the Px component now? Therefore, Px will be simply minus IH cross dou by dou x. So, Px operator is IH cross dou by dou x. What is Py operator? Py operator is minus IH cross dou by dou y. Pz operator is minus IH cross dou by dou z. Right. So accordingly, you can write here I, what I equal to complex number, right? Root of minus 1. Not here, in this context, here it is I cap, j cap, k cap, all these are unit vectors along the x direction, y direction and z direction, right. Here it is I equal to root of minus 1, such that I square equal to minus 1. This is a complex, right, clear? Any question? Right. Now I want you to try this. I will give you some time. So we have been working out with the commutators, right? So can we write the commutator involving let's say L, Z and X. So what is this? This is equal to, what is the meaning? L is the times of X, X minus L. Let's not put this in bracket. L is X minus X L is. And you know what is L is it? What is L is it? L is it is, so now L is that operator, right? You know that what is L is that operator, write that and evaluate the commutator. 5 minutes. X is X, right? So you know L is it. So this becomes, this is equal to L is that I am writing, L is that is XPY minus YPX comma X, right? So now you have seen several rules, right? You have seen rules. Use one of the rules here. Right, this with this, therefore this will come X comma X commutator times of Py plus this is X and this is X and this one, therefore X times of Py comma X, then the signature minus Y comma X times of Px minus Y times of Px comma X. So you have seen those rules, right? A, B comma C and then A comma B, C. These are the general commutation rules. So what will happen? So what is this? See, you should know this quantity. X comma X, this commutator. What is this? X minus XX. Therefore, X commutes with itself. Similarly, Px comma Px, right? Px, Px. Therefore, it is 0. Px commutes with itself, right? Therefore, evaluate this. What's the answer? 0. Anybody else? He says 0. So this goes, right? What is this? See, look at this. Let's evaluate this. Pyx, this commutator I am going to evaluate. So this is Pyx minus Xpy. Now I operate Pyx, let psi is some function, Pyx psi minus Xpy psi. So this operator here is minus I h cross dou by dou y x times of psi minus x into I h cross dou by dou y of psi. Right, what will happen? Can you differentiate? This is a partial derivative. Partial derivative of x with respect to y is what you have to do when you take the partial derivative of it is 0, right? Do you remember partial derivatives? Right. So let me come back to that. Alright, this quantity minus IH cross. So this will be UV rule. Dou x by dou y is 0. So therefore this vanishes. Therefore I will have a minus IH cross dou psi by dou y. So x and then IH cross, alright, minus IH cross, therefore this will become plus IH cross dou psi by dou y times of x. Therefore this quantity vanishes. Pyx is 0, this is also 0, right? Therefore what you will get? What is this quantity? Pxx is what? Evaluate Pxx. Minus xpx is what? Or pxx what? Again try the same method, right? If you don't know, if you can't remember the value, so it's the same idea. Pxx xpx operate with the psi. Replace this by IH cross dou by dou x x psi minus IH cross, therefore plus IH cross dou by dou x of psi. So this will become minus IH cross UV rule dou by dou x of psi plus minus IH cross psi, take it outside, differentiate, you will get 1 plus IH cross s dou by dou x. Therefore this goes, therefore you will have a IH cross minus IH cross, therefore Px comma x equal to minus IH cross. Therefore Pxx commutator equal to minus IH cross, right? Therefore this commutator, right, you will get it as minus y times of Px comma x, therefore you will get it as plus IH cross y. This is the answer. L is at x equal to this. Clear? Therefore we can write, we can generalize this. Therefore we can generalize this like this. L is at Lx comma x Lx comma x equal to IH cross y, sorry, Lz comma x is this, Lzy equal to minus IH cross x, Lzz equal to 0. So, you can generalize these commutators. Similarly, instead of x I can have the momenta component Lz px, Lz px equal to IH cross py, Lz py equal to minus IH cross px, Lz pz equal to 0. So, these are the examples that you have to work out, alright. So, I have done for one Lx, Lzx, you can try for the remaining. What about this? That is also 0, right? Xy minus yx equal to 0 because it is a scalar multiplication and nobody asked, right. So, we started with commutator bracket involving position and momenta, and we used the operator correspondence, replaced the momenta by the corresponding differential operator. Position, it is a scalar multiplication. So, replace that. So, entire quantum mechanics is built based on the commutator brackets, alright. You can have in terms of, you can work with the differential equations or you can work with the commutator brackets. So, this is a very important area in quantum mechanics, right. Why angular momentum? Because it results from the motion of a particle. So, we are looking at only one particle, but this is also valid for collection of particles when you have the total angular momentum. Similarly, the spin also important, therefore, you will have a spin angular momentum. The algebra that you are working out for the angular momentum, right, L, is also valid for the spin of the electron also, spin of the particle also it is valid. Therefore, we generally generalize, there is something called general angular momentum, right. We won't call it as L or we won't call it as S, but we call it as a J. Some physics book uses capital J as the angular momentum. Some chemist book, for example, in the case of Levine, they uses capital M as the generalized angular momentum. That M represents the angular momentum L or angular momentum S, alright, these are all possible. One of the important, in the case of, let me work with the L, you have L square. So, L is an angular momentum vector, therefore, L you dot with L, then you get a L square. A dot A is a square. Here it is something similar to this, the modulus of the angular momentum vector, alright, this is a modulus of the angular momentum vector. Your L vector is what? Lxi plus Lyj Lzk, that is what you are using. Therefore, your L dot L square, right, you will have a dot product of Lxi, Lyj, Lzk with Lxi plus Lyj plus Lzk, same, right. Therefore, what you will get? You will get L square plus Ly square plus Lz square, right. this. Let me use this. Therefore, your L square operator is, sorry, L square is Lx square plus Ly square plus Lz square. All right. Now, we are going to play with this. We'll work on this algebra for some time. Very important. And angular momentum is manifested, or angular momentum is implicated in your rotational spectra. Definitely Mangal Sundar sir will, I think he would have discussed microwave spectra, all right. So he will definitely discuss about L. I want you to try what is the commutator of L square with Lx. Here no new chemistry, no new physics, right? It's just algebra. That is why these are all called operator algebra. Give me the answer. Don't give me 0. If you give me 0, I'll be happy. Yeah, don't make, because these are all recorded, therefore don't make noise. But discuss within yourself very in a what is this? This is Lx square, Ly square plus Ll square, comma Lx. This is the commutator. So this will become Lx square comma Lx plus Ly square comma Lx plus Lz square comma Lx. So remaining, I am leaving it to you. You are familiar already. This term is 0. Therefore, you will have Ly square comma Lx plus Lz square comma Lx. Now use the general formula here, AB comma C, AB comma C, that formula. This becomes Ly Lx times of Ly plus Ly times of Ly comma Lx plus Lz comma Lx times of Lz plus Lz times of Lz comma Lx. We have already defined Lx comma Ly equal to IH cross Lz. It's a cyclically you can permute. You will get the commutators, right? Therefore, this will become Ly Lx. Lx comma Ly is minus IS cross Lz. Therefore, this is minus IH cross Lz Ly. Ly is here. Ly Lx x comma y is Lz. Therefore, this is minus IH cross Lz plus this Zx. Alright, this quantity is Z, X, Lz, Z, Lx. Take care of that. So this is I, H cross, Ly, Lz, Lz times of IH cross Ly. Therefore, you can see that which terms are cancelling. IH cross Lz, Ly, IH cross Lz, Ly minus IH cross Ly Lz plus IH cross Ly Lz. Therefore, 0. Therefore, this tells you that L square comma Lx equal to 0. Any surprise here? Nothing. All right. What about this? Now again we can generalize. Therefore, L square Lx equal to L square Ly, L square Lz to 0. So, let me summarize here. So, we defined angular momentum taking from the classical expression r cross p and then replaced minus IH cross dou by dou x for the x component to convert that into the quantum mechanical operator, right. Therefore, you get minus IH cross dou by dou x. Py similarly you replace with the minus IH cross replace dou by dou y. Pz also you replace with minus IH cross dou by dou z. Remember this operator correspondence, very important concept in quantum mechanics, right. If you want to try any problems, you need this fundamental idea. So, using this we have defined the corresponding angular momentum operators. We defined L, Ls I, Lyj plus Lzk, right, this is the operator. Then we defined L square plus Ly square plus Lz square. This is simply the scalar product of L with L, right. It also gives you the magnitude value of the angular momentum, right. Generally we represent magnitude of this value by this. Therefore, this is the magnitude value. The basically this is something similar to the length of a vector, right. Then we worked out the commutations involving these operators, very important. So let me write all the important commutation relations involving angular momentum. All right. So what are the important definitions of these angular momentum operators? So they are Lz comma x. What is that value? IH cross y. Right. Lz comma y minus IH cross x. Lz comma z equal to 0. Correspondingly, we can write for the Px Lz with the Px component. What is that? I cross IH cross Py. Lz Py. What is that? Minus IH cross Px. Lz with the Pz equal to 0. So 5 minutes time, I won't derive this, prove this to commutators. Take. So that is also 0. We have proved that. Now try the last two quick. I want you to prove that Lz equal to 0, Lz Px also equal to 0. Let me start with the Schrodinger equation. Right. Now again we'll look at the Schrodinger equation in terms of the operators. Right. So what is this operator? You must have seen many times in your MSc class. This is your Hamiltonian. So what is Hamiltonian? Hamiltonian represents the total energy of the system. It is an operator which represents the total energy of the system. Total energy means what? You have a kinetic energy plus potential energy. So that's the total energy here. Kinetic energy of the particle and potential energy of the particle. I have two particles. Let us consider two particles. Two particles with the masses m1 and m2 and charges E1 and E2 units, right? I am not specifying what units, but according to the units. So these are the two particles that we are considering, all right. So I take this as the reference coordinate system. I have this particle 1, I have a particle this is a vector r1, this is a vector r2, all right. And the distance between the two particle is particle 1 is p1, this is p2, mass is m1, mass is m2. The distance between them is r12, which is r2. If you take this, then this is r2 minus r1. Vector algebra, take care of that. Alright. So these are all two particles with the charges. So what is the total energy now? The total energy is kinetic energy of the particle 1 plus kinetic energy of the particle 2. Therefore, kinetic energy is half m v1 square plus half m v2 square, m1 v1 square, m2 v2 square. This is mass m1, this is mass m2. Plus, they are in a Coulombic potential because you have they have a charges. Particle 1 has a charge E1, another one has a charge E2, right? So, it may be Coulombic attraction or repulsion. I put E1, E2, therefore, I am writing E1, E2 divided by R12, the distance between the two particles. This is Coulomb's law. The force of attraction or of repulsion between the two charges are directly proportional to the product of the charges and inversely proportional to the square of the distance. And the potential is directly proportional to the product divided by the distance, right? So, you are all familiar with this. Therefore, total energy is half m1 v1 square plus m2 v2 square, E1 E2 divided by R12. But in quantum mechanics, we convert them into, because we have only these, we have a position and momenta. We work in this basis x comma p, alright. We work in these two conjugate coordinates. Therefore, I want to convert this into p1 square by 2m plus p2 square by 2m on m2 plus E1 E2 divided by R12. So, this is my total energy H. Classical Hamiltonian is this. This is classical. I am going to convert this into quantum mechanics, quantum mechanical operator, alright. Therefore, this becomes, H operator becomes minus H square del 1 square by 2m1 minus H square del 2 square by 2m plus E1 E2 divided by R12. So, this is the corresponding quantum. Generally, we won't write like this. This is for your understanding, I am writing. So, when you have the classical expression, convert them to corresponding quantum mechanical by replacing with the corresponding differential operator. So, for the P1, operator is del 1 square minus H square by del 1 square is the corresponding operator. For P2, del 2 is the operator, right, replace with the corresponding operators, right. Now, next step is, you are going to write the Schrodinger equation. What is Schrodinger equation? H psi equal to E psi is a vector, alright. Psi is a vector. Remember that it is a n-dimensional vector. How do you write this? What is E? What is the operator corresponding to E? The operator corresponding to E is IH dou by dou T. Therefore, this equation becomes H psi, therefore IH cross dou psi by dou T, right. This is E psi, H psi portion, that is minus H square by 2m1 del 1 square minus H square by 2m2 del 2 square plus E1 E2 R12 times of the wave function. This is the Schrodinger equation, time dependent. You will see that there is a time here. This is the time dependent Schrodinger equation of two particles having charges E1 and E2. So, your wave function, the solution to this equation psi will be a function of x y, z as well as time. So, it is a function of all the coordinates, two particles, therefore, you will have, it is a function of, because it is a two particle, therefore, you will have coordinates r1 vector, r2 vector and time, or if I write it in Cartesian, x1, y1, z1, x2, y2 to gamma t. So, this is the wave function of the system, which is a function of these. It is a time dependent Schrodinger equation. Generally, we look for, most of the time we look for stationary state solution, right. So, we solve time independent Schrodinger equation.
Swayam Prabha, Digital India, Educated India.